Yeah, so I'm just sharing this screen. So now I'll just briefly write everything, just not everything, just the main thing. Yeah. So we want to say that if fx minus fy is less than epsilon for all x and y beyond some point, given any epsilon, then that we want to say, let's see if this is true, that limit exists. So you can see, right, that this condition means that the value of fx cannot change too much, right? It cannot change. So the change can be made as small as we want. Have I shared the screen? Yeah. Change can be made as small as we want. That's what this is. So so one way is to try to use sequences, try to bring this to sequences and try, or just go by contradiction. I don't know if you want to. Okay, so step one, which you guys should see easily, is that f is bounded. Okay, f is bounded. So f is from R to R. Just imagining f is from R to R. Okay, f is bounded. So do you guys see that f is bounded? Okay. No. So no. So this is not. No, let's just make it R. Just make it 0 to infinity. Okay, it will still work, but let's just not. Yeah. So f is bounded. So now if something is bounded, then how do you show that its limit exists? Or what does it mean to say that the limit does not exist? Yeah, that is okay. But so some kind of thing which you can use to, so that you can use this condition, or yeah, so maybe you can try to use sequences in the sense, like, maybe, so if limit doesn't exist, then what does it mean in terms of sequences? Yeah, so this means that there are two sequences going to infinity, and there is another sequence going to infinity, such that, that's right. Yeah, so we can assume that they converge. Okay, that's Bolzano-Weierstrass. You get a convergence of sequence if they don't converge, so that's fine. So we can assume that these two have limits, but different limits. So let's say this goes to L1. And this goes to L2, a different L2. Now you should try to be able to. Okay. So if we try to draw a picture, What less than epsilon? So what do you mean? No, you have to say more precisely. I don't understand. Huh? Epsilon is not fixed. So given any epsilon, this happens. Yeah, given any epsilon, you can eventually make the values very close. You can given any epsilon, you can eventually make the values less than epsilon. The difference between the values less than epsilon. But if you can do that, then how can you have two different sequences? Right, and now that is just almost very clear, right? So if you limit, okay, I don't know what is converging to 0. But yeah, so if one of, yeah, so they have to converge to the same point, right? Because if you have these f of x1s converging to L, and then you have f of y1s converging to L1, and then this is converging to L2, then obviously the, right? I mean, then this is just always, right? So it means that you can make a small enough epsilon for L1 and a small enough epsilon for L2. And yeah, and then after some point, these f of xi's, they are in this band, but the f of yi's are in this other band, right? So then obviously their gap is more than this epsilon. And so you can take epsilon to be this gap. Right, so you can first choose a band, small bands, and then you can choose a suitable gap. Right, and then obviously that's a contradiction, because then, but this with this condition can never be met. Yeah, because these things keep coming and the difference is more. Okay, so is this argument fine? Okay, right. So basically, see, the key in this was number one, boundedness. Right? So once you have boundedness, then the second thing is that everything has a convergence subsequence. So once, I mean, you don't even need to go by contradiction actually. Okay. So once you just say that I'll pick some sequence and I will take its limit, its functional values, and I'll take a convergence subsequence. Now I'll take any other sequence. Okay, I'll take any other sequence and show that it also converges to the same place. We'll just use this condition directly and show that it also converges to the same place. Right? Then basically all subsequences converge to L1. Simple. And this is precisely the Cauchy criteria proof in the case of sequences. Okay. And here we are seeing in the case of functions. Okay. It's a simple thing, but maybe not so simple. So it's a little, I mean, for high school, I mean, if you're giving these exams, it's not maybe so simple, but it's nice. It's easy and clean. Okay. So what was the use of this? So using this last time, we said that this that was very wonderful, good result is that this converges or is bounded or converges is same because positive function was taken mod implies that this converges. And in any slightly challenging question, you will see that you'll have to use this. I mean, unless if you're using some other theorem directly, but this is kind of useful. Okay. So yeah, absolute convergence implies, okay, because you see in these kind of cases, what is happening? This is convergent and this has limit L. Yeah, we want to prove something else is convergent, but we have no idea what its limit is. Yeah, I mean, what this value is. This value can be some M which has no description from L in terms of L or something, right? Because it could be very different. Okay, so this is So, and you see, so, and this is a place where we use this criteria, right? So in any places where you just sense that, well, I cannot really find the limit, or I cannot even describe the limit in terms of what I've given. So then in the purely existential things, you use the Cauchy criteria. Yeah. So yeah. So at the end of the day, we are using Bolzano-Weierstrass, and the combinatorics part is that there is a monotonic sequence, subsequence, but the real thing is that the supremum property, that we have the supremum of a set. Yeah, that leads to the Bolzano-Weierstrass. Okay. So anyways, and all of these are same. In fact, one can prove Bolzano-Weierstrass from Cauchy criteria. Okay, that is also there, but yeah. So that was a good result, I think. Now let's actually move to one differential equation question. So this is a question which I had given last time. Let me just see. So it was, and there was other integration question. 1 second. So where was the question? Yeah, so it was this question, I suppose. So this is, so last time we saw some second order differential equations which look like second order, but they were really not second order. Okay. We could convert them to first order, or we could find them as d of something and do integration. So those were the things. And now this is, let's see if what this is and how we can see this. So if I put this equal to 0, then also we kind of did it, but let's just go with, let's change, let's do this. Okay, let's try to think about this. So let's just put some initial conditions. So find, so this is more like an illustrative one because maybe you don't know all the things, or I don't know, let's see. I mean, but at least you should be able to get the answer. Find, find all solutions given, you could take anything, you can actually take anything. Yeah. So maybe first you can try guessing solutions or things like that. So what will the be? What will it be? Sorry. Okay. Okay. Yeah. Y triple dash is equal. No. So yeah. So you, I mean, I don't know if it's third differentiable. At 0 only, we can say something. So Rasubru, what can you guess one solution list? So if you're able to guess solution for the homogeneous case, then why can't we guess solution for this case? So it's simple. Mm-hmm. And okay, 4x. Huh. No, no, no. 4x is a little strange. Okay. Yeah. Yeah. Only 4 is okay. 4x you can see is strange because you'll just get, yeah, because y is here. And this works. Good. Yeah, that is right. Right. So let's just find it. Let's just do this calculation quickly. So okay, let me check it also. Hmm. So and what is A? Yeah, so that's 1, right? A is 1. So what we are getting is yeah, so that's what we have to think, but at least we have the answer, right? So I mean, what the technique that we are learning is that this non-homogeneous part, we should not throw us off. We can just translate the solution, and we should keep that in mind. Is all I'm saying first. But then we have to reason why are these all the solutions and so on. Okay. So let us make, so there is a theorem that I can tell you, and that is if you have a second order linear differential equation. Okay. So what does it mean? Second order and then linear differential equation. What does it look like? Second order means that the highest derivative is second, and then first derivative, then this, and then maybe no derivative, right? And what does the linear mean? Anyone? This is the basic thing. What does the linear mean in this case? A linear means that the degree, yeah, yeah, and maybe Suru, you were saying the same thing, but in general, yeah, it shouldn't be any multiplication of two derivatives or y dash and y double dash. These things should not be multiplied. So all the derivations should be, just lone standing. And yeah, so then we can just look at So we can have Px, we can have Qx, we can have Rx, or functions of x, right? And so this is the general picture because you can divide by the P, this thing usually, but anyways, fine. But what we are looking at is a special case, right? It's a Rx is -4, Qx is 1, Px is 0. That's our equation. Now the thing is that any second order linear differential equation, first of all, has solutions. Okay, this always has solutions. This is not what we will prove. We cannot prove this is a hard theorem. But it's interesting that it has solutions. Okay. Yeah, I mean, there are some conditions on PXQs, but at least if you take constant coefficients, then it has solutions in our case. But more importantly, given given boundary value, in the sense that maybe I should not say boundary value, I should just say initial condition. Given y naught and y derivative at y naught and y naught, given these two things, this is a theorem that says that there is a unique solution. This is not useful. Quoting these theorems and I'm just telling you will prove certain things which will give some good, be some good problems. So there is a unique solution. So at least this means that knowing this means that once you can guess a solution, if there are these remember boundary values has to be like this. Telling you y0 and y1 is doesn't count as a boundary value. Okay, so okay, that's not what I'm saying. Let's forget about boundary value. If this is given, if y at 0 and its derivative at 0 is given, then there is a unique solution. Okay, so with all this, we can say we are done. Okay, but let us take it little forward. Okay, so let's forget about initial conditions altogether and try to analyze. And you see, there is a lot of similarity with linear equations theory, matrix theory. There is a lot of similarity. That's what I want to just say a little bit. So if there are no initial conditions, then what? Let's just say that we have an equation like this. Let's just say that we have an equation like this. So 5 y prime y equal to 10. So I'm not asking to solve it. Okay, let's just try to think, just check it and think. We will eventually maybe solve this. So let's say there are no initial conditions given. So if no initial conditions are given, so if no initial conditions given, okay, then how does a solution look like? Okay, so here is a problem, okay, which you can try. Let's say this equation is given. Okay, I'm not trying to solve it. Okay, but this is a problem. If y1 is a solution to 1, okay, and y is a solution to y is a general solution, is a general solution to the homogenized one part, is a general solution to this. This is just very similar to how we solve equations. Solution to this, then y1 plus y is a I don't say I just mean that it represents general solutions. Is general solution means it represents all solutions. Is general solution for 1. This is a very not very difficult but nice problem in differential equation. So basically it's saying that if you guess one solution, then that's enough. If you can guess one solution, then any solution of any other solution of this equation can be gotten by adding a solution, adding solutions of this to the guess through one guess. So you have to guess one solution for this one and have to find all solutions for this, and that will give you all solutions for one. So so you try to do this. This is not hard. You can try to think about matrices and so on. Ax plus dy plus cz equal to 4. If you instead just guess one solution, then how do you find all solutions? Using that guess solution. Okay. Or I can write here that if S is set of all solutions to 2, okay, then maybe this is more clear, is set of all solutions to 1. These are the questions that can appear, because these don't involve any techniques too, but these are nice. So it's very straightforward actually. You just say that something y2 is another solution, then y2 is another solution of 1, then how do you yeah, anyone? Is it too what abstract, or what is it like? So what I'm just saying is y1 satisfies this initial equation. So y1 is a solution to the initial equation, and we don't need to know y1. Okay, just this. And now if y2 is another, so this is like I'm almost doing the question. If y2 is another solution of 1, I'll just, yeah, it's already written, everything is written. Then so how do you get to equation 2? How do you get to the homogenized equation from here? And this is this what we are doing here. This kind of thing happens everywhere. Whenever you have to find all solutions to some equation, or to differential equation, linear equation, or some all possibilities in something situation, then just solve the homogeneous part and guess a solution for the non-homogeneous part. Okay, I will try to show a different view, but first let us just do this. We should just do this first, then we can. There is a good reason why it works very well. So how do you get to a solution of 2 from these two equations, last equations that I've written. Come on. So we know this fact that if y1 and y1 is a solution of 2 and y2 was a solution of 2, if then the sum is also a solution and difference is also a solution and so on. But in this case, that is not the case. But what happens if you take the difference? Right? But you'll get 20, right, on the right hand side, right? So you take the difference. Yeah, right, because you want to relate this to this solutions of 2. Okay? You want to relate it to solutions of 2, right? So that's why you have to just subtract. So it means that y1 minus y2 is a, and you know this is a solution of 2, right? So it means that y1 minus y2 belongs to S, right? So you can say that, yeah, or you can just take y2 minus y, it doesn't matter, but yeah, y2 minus y1 belongs to S, right? Same thing. What does it mean? It means that y2 is equal to y1 plus something in S, some solution of S, which is what I wanted to show. Y2 was an arbitrary solution of the second, y2 was an arbitrary second, some other solution, arbitrary other solution of equation 1. And we are showing that it just gotten by, guessing a solution y1 and just adding to it all possible solutions of. Right. Okay. It's also like obvious, right? If you just take some y3 to be solution of this and add 1 and 2, you get another solution of 1, right? But you get all solutions of 1 like this because of the reversibility, because we are able to subtract and get back. Okay, this is not a difficult question, but it's a, yeah, it's a nice. So is this fine? Right? No, yeah, that's fine. That is there. We will see that if it is difficult, but at least you have a, that if you guess, then it's good. And so maybe, yeah, they can, if it's a part question, they can tell you, but in fact, this guessing is not difficult. So can anybody guess a solution, please, since we are already somewhere, and since you have said, so it's not difficult to guess. Just guess. No, just guess, simple, just guess, meaning you can take y equal to 10. Right? Okay, so guessing is simple, that's fine. You missed it, that's okay, that's just a small thing. So yeah, it works. Yeah, that's the beauty of this, right? The simplest solutions can be like this, right? So for some initial values, you can imagine that the A and B is such that it cancels and so on. It works. Yeah, it certainly works, right? So now you understand what these kind of things will work. Yes, and then you need to then just shift focus to this. Okay, that's the beauty of this method. But I'm not telling you to just you learn a new method. No, the proof is an interesting argument. Okay, simple problem. Okay, but I just want to show just an interesting view here. So what is basically happening is, if you imagine a linear equation, so this is just a, so let's say you're imagining 5z. Well, I could just say it's 2 variable also, but let's say this. Okay, so what is the solutions of this? It's just a hyperplane, right? You guys know this. It's just a plane in 3-dimensional space. Yeah, it's a plane in 3-dimensional space, but it doesn't obviously pass through 0. Okay, so if I take any point in the plane, yeah, then you can imagine that if I take this plane, so if I take this plane S and I shift this plane to the origin parallelly, I shift this plane so that it passes through the origin parallelly. Okay, I mean parallel to this plane, and it passes through the origin. If I shift it, which basically means if I look at solutions of this, right, then using using solutions there, I can get all solutions of this plane if I just know one solution on this plane. So what I mean is if I have two parallel planes, right? Two parallel planes. And if you know one point in this plane, if you want to get the other point, right? So there is this, there is the origin. Yeah. You want to get to the other point. So yeah, right. So this is the origin. You know one solution. So this is one solution. You want to get to the other solution, right? So you can. What I'm trying to say is that you can. So you can take one solution. This is one vector from the origin. So how do you get to this? You see, you have to just add this vector, right, to get to the other solution in the top plane. But that just means you have to, you can just take this parallel vector, translate that vector here, right? In the homogeneous version, in the plane that passes through the origin, you take a vector there, which means you take a solution there, and you add it to this this guess solution, and that when you add, you get the other solution. And in this way, you can get x0 plus ab. Yeah, very good. Yeah, so there also we do a similar thing, right? We guess one solution, and to find all solutions, we just take a solution of ax plus by equal to 0. No, some like all solutions of ax plus by equal to 0, right? And we basically add them. We put a parameter so that we know, and we get all solutions. Yeah, that's another place where we use this. That is very good. So you see, this is basically what is happening, and just pictorially it's happening, and so it kind of happens here. Differential equation. I mean, all this can be said in one place, linear algebra. These are cosets, but that is not that's not the point. This is simple problem. Okay. And yeah, so just keep this in mind because it's easy to prove, but the technique is interesting. Okay. So probably if you see some linear algebra handout for Olympiad or something, this will certainly be mentioned. Okay. But anyways, the point is, let's now we want to talk about the homogeneous part. Okay, so obviously like e to the power of other thing, let's see, and what we can say. And there also some trick and then some problem which will resolve some theory. Okay. So point is that we can now shift focus to the, so guessing the solution, there is no guarantee that it will be easy. In this case, it was easy. There are many things in this theory, but those are not needed. But and neither do I know them. So I had studied them, but I used to hate the subject because I didn't like the teacher so much. Okay. So I didn't learn this subject at all. I got very bad in this. And that kind of was a very bad time. That teacher, and it's bad. I lost interest in analysis after that. But yeah, not lost interest, but okay. No. So in CMI initially, first, so basically the CMI differential equations course is supposed to be good differential equations. Okay, I mean what obviously, but in the first week they just solve the simple things, right? I mean first 1 or 2 weeks they just do basic high school stuff. Okay, that's but from a more first 2 weeks they do. Obviously after that do more things, many more things. But this teacher did mostly high school stuff till mid-sem, or I think till end-sem. Very strange. Okay, big the calculations just got bigger and bigger. Okay, strange. And yeah, anyways, that's So in any course, even if we do linear algebra, you'll see that first it depends on the teacher. First few weeks will be what you already know. Okay, yeah, and group theory maybe not. But yeah, it's like analysis. You will see the first semester. So what analysis is discussed, you will see first semester at least will be mostly that. A little bit more maybe, but again, it depends on the teacher. Depends a lot. Yeah. It is like that. In discrete maths, you will see almost okay. It will be like that, at least till midsem, I think. If you, that's the thing. Okay. But obviously things are done in yeah, general setting. So let us then try to so we can just take this itself and try to think. So now let's try to guess solutions for this. Let's see, and then what we can say. The e to the power thing is the thing, I think. So you can think along those lines. Yes, right, something like that. So, but okay. So you're getting e to the power -5 plus So this is one solution, and similarly a minus, right? Let's just write it separately. Yeah. So you see, this is very easy to get because basically you will see that it just boils down to solving this. Once you put the e to the power, then you will see it. I'm putting the coefficients 1, 5, and 1. Just copying the coefficients. Okay. So whenever there are constant coefficients in the original differential equation, then you get this characteristic polynomial. The same thing happens in linear recurrence because they are also like derivatives. They are discrete derivatives. So this way we can guess these two solutions. So you can see you can always guess these two. So then what will the general solution look like up to what you can say? Yeah, and it's all linear combinations of them, right? So we have, we have forgotten the initial conditions thing here because that you can always put and get the specific solution, and I've told you a result along that line. And then second was the one with a constant on one side, non-homogeneous, that also we have resolved and reduced to this. Now here we can say so far that these look like, so I should have chosen a good, but that's fine. Let's just write this. You think no, it will be down, right? Because you have found the exponents to be that only, right? So, but how can we say that there are, so maybe is this a good question to ask? Yeah, let's at least put it on the paper, put it here and see. So why are there no more solutions? This is a good, and this is a good elementary calculus question. Don't think that this is some theory. Whatever is theory, whatever is hard, I've told you it's hard, so you can leave that. But this is good question. Why are there no more solutions? Okay, so let's not answer this question now, but let me just give you another. No. So you think you're mixing it up. So I did not say this, right? I said that if there is a solution for, let's say you put a constant 10, and if you find one solution for that, then any other solution will be that solution plus any solutions of the homogeneous version, right? But any solutions of homogeneous version, we have not yet commented on that, right? right? Any solutions of the homogeneous version, we have not yet commented on that. That is right. So we think that it should be like this, and you guys would have seen this is it, but why are there no more solutions? We have to still explain this. Okay. So this is something that you can think it's not a difficult question, but let me ask a simpler question rather. Okay. So find solutions to this. Stuck. Yeah. Yeah. E to the power x is certainly a solution, but then now how do you find more solutions? Oh, that's okay. But this is now, this looks insufficient, right? This just looks one dimensional. So try to guess another solution. Let's see if you can do that. There is, yeah, like a different solution. Because in this case, you when you saw that quadratic, it has repeated roots. So you have to find some other solution somehow. So you can try to think, yeah, you can similar to e to the power x, but there will be, like, for example, if I give you this, then how do you find all solutions to this? So just maybe saying that an equal to 1 does not work, right? That's certainly a solution, but then there are other solutions as well. Like, yes, n equal to n is also a solution. Yeah. So let's keep this part for homework. So guess the other solution. You can use analogy from here, and then you will surely get an answer. If you try to take similar equations, maybe more interesting ones, recurrence equations and see solutions, and then you can guess other solution. This is a good thing to try out. Okay. But now let us try to come back to this one. So you keep this homework. So why are there no other solutions? Yeah, that's a very interesting question. Okay. So in general, what I want to say is that if so we'll just try to prove this fact. I mean, you could do it from here, but to do it in clean is a good problem. So we'll not do that in complete details, okay? Because I'll leave parts of it like for. Let's see. So my point is that if y1, y1x, and y2x are two solutions which are linearly independent, okay, which what I mean is that such that y1, so maybe if I state like this, then you guys can try to solve this, is not a constant, it's not equal to a constant. So one is not a constant multiple of the other. You see last those two solutions, that's what the case, right? Because obviously constant multiple of the other that we can just generate from y1 itself. Yeah, if y2 was a multiple of it, vice versa, or same thing. So if this is not a constant, yeah, then any y3, we want to say that any y3 is equal to, you know, sum a1 y1 plus a2 y2. Any third solution would be a combination of these two solutions. Okay. Independent. Okay. Yeah. Right. Okay. Yes, that's what you were saying. Yeah. Okay. Okay. Yeah. But now we're trying to prove this. So I don't know how to prove this actually. No, I don't know. So let's see. So any solution y3 will be a combination of these two solutions. So let's write the equations. Let's try to get inspiration from linear equation theory, shall we? Right, because that seems to be the something that we understand a little bit. So what we are given is that no, it has nothing to do with theory. These are just real numbers, real combinations, right? Why integers are very far from here? That's not the case. No, I mean, these are numbers. A1 and A2 are numbers. So you cannot write any Y3 like this a priori, right? You don't know, but in this case, we are saying it's possible that's the case. And basically, we are saying that second order linear differential equations, the set of solutions is two-dimensional. There are two independent functions which give everything. That's the high level way to say it. Okay, but that's not useful. Okay, here. So let's just treat it as a problem. So this is a solution. And this is very less discussed. Usually we just focus on solving and solving and solving. But there is a lot of interesting, easy theory which one can discuss. So these are two solutions. And let's say that Y3 is another solution. Okay. Any solution, Y3. So Y3 is another solution. So as you said, like contradiction. So we can try to think like that. I don't know. Let's see. We want to say that the Y3 is dependent on Y1 and Y2. So if that is not the case, so no, that's what, why should it be k into Y1? That's what we are trying to prove. So that is exactly what we're trying to prove. So once again, so we know that, so basically we know that yeah, so we at least know that these two, this Y1 and Y2 are linearly independent, right? Y1 and Y2 are linearly independent. And Maybe I'm not framing it properly. So if y1 and y2 are two linearly independent, so solutions, any y3, let me just look at the statement. So maybe I'm not framing it well. 1 minute. So the statement is that if y1 and y2 are linear independent solutions, then this is a general solution. The linear combination is a general solution, and in the sense that every solution can be written that way. So if yx is any solution, then we must show, that's what I'm trying to do. Strange thing. Sorry. This is a little tricky. Yeah. Sorry. So I think, yeah, not so good, right? So let me still say it since we are doing it. So I forgot that so this involves something. I mistook it. No. So what we want to say, we want to say that y3 is equal to this, right? There is a, so given any y3, it is equal to a y1 plus a2 y2, right? But for this, all we need to show is that y3 at 0 matches with this. So this is again a beautiful thing, right? That if it matches at 0, yeah, and if the derivatives match at 0, then that's it. Then that implies, so I'm saying that the